Okay, welcome to lecture 28. So in this lecture, we're going to cover, or at least begin to cover, how we can solve homogeneous linear systems with constant coefficients. So here we have a system of n linear equations with constant coefficients, but the key point is that we are dealing with homogeneous systems. So basically, in lecture 27, we basically introduced the fact that the general solution to the non-homogeneous system of equations was the sum of a complementary part and a particular solution, in the same way as we learned in Unit 2 for the scalar case. But now we're going to learn how do we actually find that complementary solution for homogeneous linear systems with constant coefficients. Okay, so again, in fact, in the same way as in Unit 2, we're going to find that there are three cases. And today we're going to get through two of those cases, or at least most of two of those cases. So let's consider the homogeneous system of linear ODEs. So remember here, X is the vector of dependent variables, and A is the coefficient matrix, which in this case we are taking to be a constant n by n matrix. Okay, so there are n equations in this system, so A has to be an n by n matrix. For the scalar case, when we had only one second order ODE, we used the trial function x of t equals e to the lambda t to solve this system. For the systematic case, so the case where you have a system of ODEs, we're going to try to find a solution vector of this form. So x of t is our solution vector equals some vector k, I'm calling this k here, times e to the lambda t. So really what we've done here is we've taken our trial function from the scalar case and we've vectorized it just by multiplying it by some vector. K is a constant vector as well. So let's differentiate this solution vector x of t here. Well, the only place the variable appears is in the exponential. So if we differentiate that exponential, we should get this constant vector k times lambda times e to the lambda t. Okay, but we also know from the ODE that x prime, the derivative of x, is equal to this matrix A times the vector of dependent variables x. Okay, so this thing is equal to A times x. Okay, but x I'm going to write as k times e to the lambda t, because that is my trial function for x. Okay, so just to show you, this part in green here came from differentiating this trial function, whereas this part in red came from the definition that x prime is equal to a times x. Okay, so I can divide through by the exponential terms on both sides here, because that's never going to be 0 for finite t. So I get a, the matrix A times the vector k is equal to the constant lambda times the vector k. Of course, I can rearrange this, and you may recognize this system of n linear equations here. So A minus lambda I times k equals the 0 vector. You may recognize this equation, right? I is the n by n identity matrix. Yeah, yeah, I is the n by n identity matrix. And so if you recognize this equation, you probably took linear algebra in first year, because therefore we say lambda is an eigenvalue of the matrix A, and k is the associated eigenvector. So it turns out that, well, okay, this is the n by n identity matrix. It turns out that to solve a homogeneous system of linear ODEs, represented above here, we have to find the eigenvalues and the eigenvectors of this coefficient matrix, which in this case is a constant, A. Okay. And so how do we find this k? Well, recall that for a homogeneous system of n linear equations, it has a non-trivial solution if and only if the determinant of this coefficient matrix is 0. Okay, this is just something from first year linear algebra, but the point is we have to solve this, to find the eigenvalues, we have to solve this associated determinant and set that determinant equal to 0. And we call this the characteristic equation of matrix A. So just to summarize here, we have a system of n linear first-order ODEs. This coefficient matrix A, we have to calculate the eigenvalues of A by solving this determinant of A minus lambda I equals 0. And then once we have the eigenvalues, we're going to calculate the eigenvectors, K, using this second equation here. Okay, and again, we're going to have three distinct cases. And the first case is that we were able to find distinct real eigenvalues. So if the matrix A has n distinct real eigenvalues, lambda 1, lambda 2 through to lambda n, then a set of n linearly independent eigenvectors can always be found. Okay, again, this is theory from first year linear algebra. Okay, so assuming we have the eigenvalues of A are real and distinct, then we can find the associated eigenvectors, K1, K2 through to Kn, and a fundamental set of solutions to the homogeneous system of linear ODEs is given like so. So we've got x1 equals k1 times e to the lambda 1t. So the first eigenvalue, the first eigenvector. x2 is equal to k2 e to the lambda 2t, the first eigenvalue, the second eigenvalue, the second eigenvector, and so on. And of course, the general solution we learned in the previous class is just the linear combination of each of these solutions. So the distinct real eigenvalue case is probably the easiest case because all you have to do is find the eigenvalues of A, find the associated eigenvectors, and then combine into the general solution to the system of ODEs like so. So let's take a look at an example. So here we have a 3x3 system. So we have three dependent variables, x, y, and z. You can see x, y, and z appear here linearly. And some of the coefficients here are 0. And I like writing it like that because you can see, you can basically read this matrix straight off, right? The matrix A. If we write this system in matrix form, x prime equals A times x, you can immediately see that the coefficients of that make up the matrix A are 2, 5, 0, 2, 5, 0, negative 7, 10, and 5, negative 7, 10, and 5, 0, 4, and 2. So in matrix A, the first column represents the coefficients associated with x, the second column is the coefficients associated with y, and the third is the coefficients associated with z. Okay, so now what we need to do is find the eigenvalues and eigenvectors of this matrix A. So to find the eigenvalues, we have to solve this, this determinant equation, A minus lambda I equals 0. Or let's say, sorry, the determinant of A minus lambda I equals 0. Okay. So we can write this as the determinant of, on the diagonals, we subtract lambda from the terms on the diagonal. We know how to write this determinant out, right? So we learned how to take determinants of 3x3 matrices in first year linear algebra. But the point is we take this 2 minus lambda and multiply it by the determinant of the submatrix here. And then we subtract 5 and multiply 5 by the determinant of the matrix negative 7, 0, 5, and 2 minus lambda. And then we have a 0 in the last column, so in fact, we get nothing there. So if I do that, if I take that determinant of that 3x3 matrix, I can notice that in every term here, I have a 2 minus lambda multiplying this, 2 minus lambda multiplying this term, and a 2 minus lambda multiplying this last term here. So clearly, one of the eigenvalues, which makes this equation equal to 0, is going to be lambda equal to 2. So I'm going to say lambda 1 equals 2. Okay, well, if I pull out that common factor of 2 minus lambda, I can write this equation as 2 minus lambda multiplied by a quadratic, And I can reduce that quadratic into the product of two linear terms. And clearly I can see then that my three eigenvalues of this case are going to be lambda 1 equals 2, which we already found, lambda 2 equals 5, and lambda 3 equals 7. These are real and distinct eigenvalues, so we're guaranteed to have three associated eigenvectors as well. So let's find the associated eigenvectors. Let's start with lambda 1 equals 2. So to find the eigenvectors, I have to solve this equation a minus lambda I times the eigenvector that we're trying to find k equals the 0 vector. Okay, so if I do that, a minus lambda 1 times I times k1, which we're trying to find, equals the 0 vector, I can write that like so. So 2 minus 2 is 0, 10 minus 2 is 8, 2 minus 2 is 0, times this vector, eigenvector k1, which I'm going to write as k1, k2, and k3, equals the 0 vector. So what we're going to do now is just read off each line, and I might start on the bottom line. What this line is saying is that 0 times k1 plus 5 times k2 plus 0 times k3 equals 0. Or in other words, this is telling me that k2 is equal to 0. I could also have used the top line, of course. 0 times k1 minus 7 times k2 plus 0 times k3 equals 0 would still also give me k2 equals 0. Okay, looking at the middle line now, if I read off what this says, 5 times k1 plus 8 times k2, well, k2 is 0, so let's ignore that. So 5 times k1 plus 4 times k3 equals 0. So I can write k1 in terms of k3, okay, which allows me to write the eigenvector for this case, for this eigenvalue, as k1 equals negative 4, k2 equals 0, k3 equals 5. So my eigenvector k1 associated with my eigenvalue lambda 1 is equal to negative 4, 0, 5. So k2 had to be 0, so the middle value had to be 0. K1, the first entry, had to be negative 4/5 of the third entry, k3. Okay. So I have one eigenvalue and one eigenvector so far. Let's now move on to lambda 2, the second eigenvalue. Again, we're going to calculate this a minus lambda 2i times k2 equals 0, and I can write that in matrix form like so. Okay, so now let's read off these lines one by one. So negative 3 times k1 minus 7 times k2 plus 0 times k3 equals 0, so we get this equation here. 5 times k1 plus 5 times k2 plus 4 times k3 equals 0, so we get this equation here. And finally, 0 times k1 plus 5 times k2 minus 3 times k3 equals 0, or this equation here. So from that first equation, from this first equation, I can write k1 in terms of k2, and from this bottom equation here, I can write k3 in terms of k2. So therefore, if I just choose k2 to be some arbitrary number, let's say 3, because it will get rid of the fractions, then my k1 would have to be negative 7, and my k3 will have to be 5. So if I choose k2 equal to 3, k1 equals negative 7, k3 equals 5, and I get this eigenvector here. Okay. So again, if you're a little bit rusty on calculating eigenvalues and eigenvectors, it's something that you can revise. But I'm just going to tell you that for the third eigenvalue, 7, this is the eigenvector that you would expect to get. So therefore, the general solution to our ODE system is just the linear combination of these three solutions. So C1, so some constant C1, times the first eigenvector K1 times e to the 2t, where the 2 is the eigenvalue, so lambda 1 equals 2, so 2t, plus C2 times K2, so the second eigenvector here, K2, times e to the 5t, where the 5 is the second eigenvalue, plus C3 times K3, the third eigenvector, times e to the 7t, where the 7 is the eigenvalue lambda 3. So again, really important that you know how to find eigenvectors and eigenvalues for this this part of the class, and feel free to revise if you don't recall that. So in the case of distinct real eigenvalues, fairly straightforward. But now we come on to repeated eigenvalues. So case 2 is a little bit more complicated. So we can have a matrix A, a coefficient matrix A, which again, remember in the case we're looking at is a constant coefficient matrix. We can have repeated eigenvalues, so an eigenvalue with multiplicity greater than 1. Okay, so what happens here? If m is a positive integer and lambda minus lambda 1 times m is a factor of the characteristic equation, which is, of course, this equation here, determinant of a minus lambda I equals 0, then lambda 1 is an eigenvalue of multiplicity m. Okay, so if we have a repeated eigenvalue, there are two things that can happen. The first thing that can happen is it may be possible to still find m linearly independent eigenvectors, k1, k2, through to km. If we can find m linearly independent eigenvectors for our m for our eigenvalue lambda 1 of multiplicity m, then the general solution to that system is actually the same as case 1. It's well, apart from that, the eigenvalue is repeated. So we have C1 times the first eigenvector times e to the lambda 1 t, so lambda 1 being the eigenvalue, plus C2 times the second eigenvector times e to the lambda 1 t, and so on. So here the only difference from case 1, in fact, is that lambda 1 is repeated m times. So if we can find m linearly independent eigenvectors, the solution is fairly straightforward. The more complicated case, though, is that there are less eigenvectors than the multiplicity of the eigenvalue. So, for example, if lambda 1 was repeated twice, so if some matrix had the same eigenvalue value twice, but we can only find one linearly independent eigenvector, then we have some challenge that we have to overcome. So m linearly independent solutions to the system are given by the eigenvector that you can find times e to the lambda 1 t. The second is then some interesting combination of those two. So some eigenvector times e to the lambda 1 t plus some other vector times t times e to the lambda 1 t, and so on through m times. So we're going to deal with this case, or let's say this subcase, in the next class. Well, you don't have to memorize this second part here. We're going to deal with that in the next class. Okay. So for now, what we're going to do is we're going to look at case 2, where we have repeated eigenvalues, but we're going to look at a case where we can find a full set of eigenvectors. Okay. So this example here, I'm going to claim, is going to have repeated eigenvalues, but we're going to be able to find a full set of eigenvectors. So, well, I have a system of 3 equations here. Okay, well, this should be x prime, y prime, and z prime. So let's just fix that. Okay, so, sorry, I just fixed that now. So we have x prime equals some linear combination of x, y, and z. So x, y, and z, of course, are the dependent variables here. And then similarly for y and z. So we can write this system of first order linear ODEs in matrix form like so. So again, the first column of A is the coefficients in front of x in the 3 equations, so 3, 2, and 4, 3, 2, 4, and so on. So I'm going to leave this to you to find the eigenvalues of this matrix. So you may like to pause this video and go and try and do that. But if you do go and do that, then you should find that lambda 1 is equal to -1 with multiplicity 2. So lambda 1 is a repeated eigenvalue. And lambda 2 is equal to 8 is a eigenvalue of multiplicity 1, so it's not repeated. So let's deal with lambda equals 8 first because, well, it's not repeated. And, well, I'm going to leave it to you to go through and prove that the eigenvector associated with lambda equals 8, which is not repeated, is 2, 1, 2. Okay. But really, because here we're interested in the repeated case, I'm going to move quickly on to the eigenvalue -1. Okay, so this is repeated. This eigenvalue of -1 has multiplicity 2. It's a repeated eigenvalue. So we're going to hope here that we can find two linearly independent eigenvectors associated with this eigenvalue. So let's look at the equation A minus lambda I times k equals 0. So A plus I times k is, so we're adding 1 onto the diagonal, so 4, 1, 4, 4, 1, 4. And let's look at this system. Well, it turns out that all these equations are equivalent, right? 4k1 times 2k2 times 4k3 equals 0. Well, that's repeated on the bottom line, but it's also just 2 times the middle line as well. So all three of these equations are equivalent, and they effectively give us 2 times k1 plus k2 plus 2 times k3 equals 0. So what I'm going to do is I'm going to define two new variables, s and t, and I'm going to let s equal k2 and t equal k3. And therefore, if I rearrange this equation, or let's say if I substitute s and t into this equation, I get 2 times k1 plus s plus 2t equals 0. Therefore, I can rearrange that for k1 to find k1 is equal to minus s over 2 minus t. So I can write my my solution there, k, my eigenvector k, as negative s over 2, s and t, which I can split up into two parts. A part that's associated with s here, and a part that's associated with t here. So in the first part here, yes, I'm missing a negative t in here, so let me fix that. Okay, so I just fixed that now. So I basically have a part that has a relation with s and t. Okay, so the parts that are associated with the variable s have negative 1/2 here, 1, and then there's no s parts in the third part of this vector here. The parts that are associated with t, well, I have negative t here, 0 t's here, and 1 here. So that's why I get negative 1, 0, 1 in this vector here. Okay. So let's just let s equal 3 and t equal 1, and then we'll see what we get here. Then I can write s actually should be equal to 2. So let's let s equal 2 and t equal 1, and then we get this first vector here is going to be negative 1, 2, 0, and the second vector is just going to be 1, 0, 1. So these are two linearly independent eigenvectors associated with this eigenvalue of negative 1. So we have an eigenvalue 8 here, which we found its eigenvector k1. We had this eigenvalue negative 1 with multiplicity 2, and we found two linearly independent eigenvectors in this case. Therefore, we can write we have a full set of linearly independent eigenvectors, and we can write the general solution as the linear combination of those three terms. So c1 times 212 e to the 8t, and then these next two terms both have the eigenvalue negative 1, so we have e to the negative t in both of these, but they have separate and linearly independent eigenvectors here. Okay, so this is the terms associated with lambda equals 8, and here are the two terms associated with lambda equals negative 1. So in the next lecture, we'll look at an example which does not have a full set of eigenvectors. And so this is a much more complicated case, but I'm going to show you how to solve that case. Thank you.